elastic potential energy of a stretched wire or a deformed body. Elastic potential energy in a stretched wire. Elastic potential energy in a stretched wire. This is a cylindrical wire. In the diagram, initial length of the cylindrical wire is L, capital L. Initial length of the cylindrical wire is capital L. A is the initial area of cross section of the wire, and a deforming force F is acted on its plane of cross section normally. Here F is the deforming force which is applied normally to the plane of cross section to elongate the wire, and this is the diagram of deformed wire or stretched wire. A prime is the final area of cross section. Deforming force F continues to act. Deforming force F continues to act to elongate the wire. A restoring force Fr. Fr is the restoring force which comes into play in the opposite direction, such that magnitude of restoring force Fr will be equal to the deforming force F. Final length increases to L prime. Final length of the wire increases to L prime. Now we can denote the change in wire. So this is the change in wire. Small l is the change in wire, where small l equal L prime minus L. Now we can denote small change in length dl. Small dl is small change in length, and initially L equals 0, and finally final elongation small l equals small l. Let F be the deforming force. F be the deforming force which is applied let F be the deforming force which is applied to the plane of cross section of a cylindrical wire of initial length L, initial length capital L, and area of cross section A, capital A. Therefore, the wire gets elongated. The wire gets elongated and its length increases by small l. The wire gets elongated and its length increases by small l. Therefore, small work done by the deforming force F for small elongation dl, small d small l dl under bracket, whereas total elongation is small l, is dw equal F.dl. dw equal F.dl. In the diagram, dl is the small elongation, and small work done for this small elongation by the deforming force is dw. We can draw the diagram again. This is a wire of length capital L. Deforming force F is applied and the wire will be elongated. Deforming force F continues to act and restoring force Fr acts in the opposite direction. Small l is the elongation or change in length of the wire due to application of this deforming force, and we can split this total elongation into a number of small elongation. dl is the small elongation, then after dl, small l is the total elongation. This is dl, small elongation. Work done for that elongation is dw. Again we can assume small elongation dl, for that work done is dw. Then dl, work done for that small elongation is dw. Therefore total work done is the summation of a number of small work dones. dw plus dw plus dw plus dot 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 equal integration dw, where limits are l equals 0 to l equal l. So at this position l equal to 0, and finally total elongation l equal to l. So dw equal F.dl, where the Young's modulus, of the material of the cylindrical wire is given by y equal F by A divided by small l by capital L. F by A is the normal stress, small l by capital L is the longitudinal strain. Therefore F equal to y A small l by capital L. dw equal F.dl, that is the small work done, and we get the expression of deforming force F equal y A L by L. F equal y A L by L. That is the expression of deforming force. Therefore dw equal y A L by L dl. Putting the expression of deforming force F in the expression of dw, we get dw equal y A small l by capital L into dl. Therefore total work done in stretching the wire, by an elongation small l is w equal integration dw 0 to small l equal integration y A small l by capital L dl 0 to small l. So at this position in the diagram L equal to 0 initially, and finally total elongation L equal to L due to application of deforming force. dw is the small elongation, and required work done for that small elongation is dw. Then again we can assume small elongation dl and work done will be dw. Again we can assume a number of small elongation dl, and dw will be the small elongation. So w equal dw plus dot 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 equal integration dw 0 to l y A by L. All are constant that are brought outside integration. So y A by L integration 0 to L L dl. Y A by L under third bracket L square by 2 0 to L. Y A by L square by 2 minus 0. Therefore W equal 1 by 2 y A L square by capital L. W equal 1 by 2 y A L square by capital L. This work done is stored as elastic potential energy. This work done is stored as elastic potential energy under bracket EP. It is denoted by EP, not U. This work done is stored as elastic potential energy under bracket W, and elastic potential energy is denoted by EP in the wire. Therefore, EP equal W. Therefore, EP equal 1 by 2 YA L square by capital L. So we get the final expression of elastic potential energy EP equal 1 by 2 YA L square by capital L. This is the elastic potential energy. Elastic potential energy stored in the wire for its elongation small l. EP equal 1 by 2 YA L square by L, half YA L square by L. Now stress is equal, that is the normal stress is equal deforming force by area of cross section. Stress equal F by A, where A is the initial area of cross section, and longitudinal strain equal L by L, small l by capital L, and volume of the wire is A dot L. In this case, volume of the wire remains constant. A is the initial area, L is the initial length. Therefore, A dot L is the volume, and F by A is stress. So now we can find the product of F by A, L by L, and A dot L. F by A into L by L into A dot L equal FL divide only FL. Now we can put the expression of F, or deforming force F, which is YA L by L into L. So finally we get YA L square by L. That means F by A into L by L into A dot L is YA L square by L. So therefore EP was 1 by 2 YA L square by L, and in place of 1 by 2 YA L square by L, we can write F by A L by L A dot L. So we get the another expression of elastic potential energy EP equal 1 by 2 into stress into strain into volume. EP equal 1 by 2 into stress into strain into volume. That is the elastic potential energy of the stretched wire. So half the product between stress, strain and volume is equivalent to elastic potential energy. Now stress is denoted by tau, which is equal to F by A. So we can find the expression of tau square by 2y into A dot L. 1 by 2y tau square A dot L. 1 by 2y, now in place of tau we can put F by A, that is F square by A square A dot L. 1 by 2y F square dot L by A. 1 by 2y YA L by L, putting the expression of F into L by A. 1 by 2 YA L square by L. That is twice square by tau square by 2y dot A dot L. Therefore, EP equal 1 by 2 YA L square by L. That was the main expression. Then putting the expression of 1 by 2 YA L square by L, we get EP equal tau square by 2y dot A dot L. So EP has three expression. Elastic potential energy has three expression. First expression is 1 by 2 YA L square by capital L, where small l is the change in length or elongation, capital L is the initial length. Second expression of EP is 1 by 2 stress into strain into volume. Third expression is tau square by 2y dot A dot L, where tau is the stress. Tau is the stress. EP equal 1 by 2 YA L square by L. EP equal tau square by 2y dot A dot L, where tau is the stress, and EP has the second expression, which is 1 by 2 stress into strain into volume. So these are the three expression of elastic potential energy of a stretched wire.